Hi, today we're talking about latent denoising diffusion probabilistic models. So the focus of our project is to create a diffusion model that is capable of generating high quality images of specific classes. In order to do that, we will incrementally implement a series of techniques, including DDPM, DDIM, VAE, and CFG, and we will learn about what improvements each of these techniques will bring to our model. So our task consists of mainly two parts. First is according to the corresponding papers, we'll implement these techniques, and then the second part is we'll explore additional techniques such as PNDM, which we'll talk about a bit later. So for our data set, we'll use ImageNet 100 data set. There are 100 classes in total, containing images of 128 by 128 pixels. So in training data set, there are 130,000 images and 5,000 in validation set. So here are some examples from the Flamingo class.
So for further implementation, we were planning on changing the scheduler to be PNDM. This is a technique that uses rogue CUDA methods to speed up calculations with no accuracy. In particular, PNDM stands for pseudo-numeric methods for diffusion models. And this gets second order derivatives of the run CUDA methods to increase calculations by 20-fold. This also does not lose in comparison to other schedulers.
And for implementing the methods that we mentioned earlier, we used CFAR 10 instead of ImageNet when implementing them because it was simply smaller, a lot less classes, which meant that we could run epochs faster and figure out if there were any errors. But at the end, you will see that our results are from ImageNet. So for training, what we did was we took the data, added transformations such as resizing and normalization, and then we took the images and put them through VAE that was already pre-trained, and we took the labels and put them through a class embedder, and we used the VAE encodings to put into the scheduler as well as noise, so that we can pass in that finally into our UNet so that it could make predictions along with the class embeddings. And at last, we calculated loss using MSE. And for the pipeline, we pretty much do something similar where we just run it through UNet for predictions and then use the scheduler to calculate previous images or images at previous time steps. Here are some images without CFG, which is classifier free guidance. As you can see, the images are not very good. That, however, is also partially on our part since we didn't run a lot of epochs because we ran out of time. Here's with CFG. As you can see that it is slightly better. Here on the right, you can kind of see like maybe like a fox face with a nose. And here are the inference results by calculating both FID and IS. As you can see that for pure noise, we have a high FID number and our IS is one mean with zero variance, or I mean zero mean and one variance respectively, since it's pure noise and it has equal variance around the bell curve. And without CFG, you can see that since we're actually training the model, the FID is lower, and also there is the mean is shifted. And with CFG, um, the FID is lower than with just pure noise. However, you'll see that it's actually higher than without CFG. We theorize that this is because CFG takes longer to converge, and at the initial steps of training, it will converge slower, but at a better result. In conclusion, DDIM and VAE grants 5 to 6 times speed up, which makes training DDPM realistic, since without it, it would take literal weeks to train. And CFG improves performance, but it takes more epochs to converge. And so we hope to implement the PNDM in order to increase speed up even further by 20 times without compromising the quality.